Welcome back everyone. In today's video, I'll be explaining AtCoder Beginner Contest 322. I'll explain the problems from C to E, not including F. I've provided the correct Python codes in the video description, so please check it out after you've listened to my explanation. I'll upload problem F as soon as it's finished, but I can't say for certain, sorry. But let's get started with problem C. We are given a list A of days fireworks will be launched. Our task is to count the remaining days until the nearest upcoming fireworks display for each day. We first make a list D from list A about whether fireworks will be launched on the day or not. Then we define our list next to record the day of fireworks afterward. We can fill it with list D like red ink. Then the answer for each day is easily computed as next of I minus I. This is the outline. Then, how do you make the list next in detail? This calls for some creativity. As you see, the next value is determined by the values of D towards the end of it. Therefore, it's not wise to determine the next value from the beginning. Instead, we should determine it from the end. I'll show you how it works. We define a new variable n as the most recent day fireworks are launched. Then we look at day 8. We have fireworks on day 8, so let n be 8 and substitute n by next of 8. Then we look at day 7. We have fireworks on day 7 again, so let n be 7 and substitute n by next of 7. Then we look at day 6, but we don't have fireworks on the day. In that case, we don't update n and we just substitute n by next of 6. We continue it with this rule. Then the algorithm works in this way. And the list next are filled correctly. This ends the explanation of problem C. Let's proceed to problem D. Our task is to fit 3 polyominoes into a 4x4 grid. Since the grid size is small, this requires brute force-like algorithm and tough coding skills. To minimize effort, we use bit manipulation technique and bit DP. We first label 16 squares from 0 to 15 and represent an arrangement of them as a 16-digit number in the binary system. So, if the first red polyomino is placed in this way, we represent the arrangement as this number below. Like this way, we fill the grid with polyominoes, and the goal is regarded as a number with 16 consecutive ones. Then, we define dp of I and bit as whether the state bit is possible or not after placing ith polyomino. We start with dp of 0 and 0 and compute dp of 1s considering all possible arrangements of the first red polyomino. We denote it x of 1 and must compute it beforehand, but we can repeat the process to get dp of 2 and dp of 3. After that, if dp of 3 and the target number is equals to 1, the answer is yes. This is the outline of the problem D. Let's discuss how to compute x of 1. We must consider all translations and rotations of this figure. I declared to use bit manipulation, but in this process we use two-dimensional coordinates. For translations, we should imagine a 4 times 4 lead frame and cut out the grid with it. Then, regarding the lead frame as a new grid, doesn't it appear as if the polyomino has moved? This is how to consider translations. So we must check all possible ways to place the lead frame on the plane. And to do that, we only fix the coordinate of the top left. And if it contains the full polyomino, add the corresponding number to x of 1. But it sometimes fails like this. So the criteria are so simple. Just count the pieces of it in the lead frame. So we easily check all translations like this way. Next is this and this. So that's all about the translations. Then how about the rotations? This is also easy with the 2D-dimensional representation. A 19-degree rotation can be represented as 3 minus y, comma x. Then we just repeat the process of translations for the direction of the polyomino. After rotating 4 times, the total process of computing x of 1 will be done. Note that the size of it is at most 7 squared times 4, and it's small enough, but in fact, the real value of the size of x of 1 is much smaller because most translations are unacceptable. We should do this process for all the polyominoes beforehand. I have the last warning about the overlap of two polyominoes. When we place the blue polyomino after the red in this way, the upper example is allowed, but the lower example is not allowed. How do we divide them? In this case, binary operation is very useful. In the upper case, the bit and operation of bit and x is 0, but in the lower case, the result is not 0, always not 0. This is because the overlapping squares remain in the calculation in this way. So, using this calculation for the transitions of dp, we've solved problem D. Then let's proceed to problem E. This is the problem of selecting the optimal combination from n plans to achieve the desired conditions with the minimum cost. The problem is structured based on a sequence of choices with two options, either selecting or not selecting for each plan. Such problem type is typical for DP. So we define DP of I and x1, x2, and xk as minimum cost to raise parameter j by xj after plan I. In general, we can't define too many variables because of the size of DP, but in this case, it's affordable. That's because n, k, and p are all small. Now, I describe the transitions of DP for your comprehension. We consider p equals 5 and start with the case all variables are 0. Then we consider both the adoption and rejection of plan 1. When adopting it, the status increased by 3, 4, 5 respectively, and the cost is 4, but when rejecting it, the status remains 0. Then we consider plan 2 in the same way, but don't forget to round down to 5 when the parameter value exceeds 5, which is the target value p, which is equal to the target value p in this example. This is needed because variables in this DP can't handle large numbers. Then we repeat the process and finally hope to reach DP of n and 5, 5, 5. This is the outline. In short, the transitions of the DP can be written in this way, but I will leave the details with you. One thing I must tell you is left. That is, too many variables throw your code. This is not about the algorithm, but about the system of computing. Especially, accessing a deeply nested list structure on Python takes a tremendous amount of time. I don't check if this introduced algorithm passes the problem, but it's quite doubtful. So for the improvement, let's compress the k variables into one. Since each variable xj ranges from 0 to p, the tuple of them can be represented as a single k-digit number in the base p plus 1 system in this way. Therefore, we only define n instead of the tuple of x1 and xk, and this is kinder for the calculation system. But for our code writing of the transitions of DP, we must know how to reconstruct x1 to xk from the number n. I'll explain about this. We first calculate the modulo p plus 1 of n and it's equivalent to the last value of x, which is x3 in this example. Then we divide n by p plus 1 and again calculate the modulo p plus 1 of it. Now we have the second to last value, which is the value of x2 in the example. We repeat this process k times and find all the values from the end. This ends the problem E. With that, I've completed all the explanations today. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.